The title of my talk is An Extended Explanation of Negative Binomial Family with Schwarzschild Effect. This is a joint work with Gauss Cordeiro. He is a very well-known statistician in Brazil, a very productive man. He's not Bayesian, but he is responsible for studying the mathematical property of the distribution I'm going to show it for you. Bazan is my colleague from the ICNC, São Carlos. I think he is presented here. No? He's there. He is responsible for the Bayesian application, illustration of the proposed model. The technique I'm going to use here is the same. Danilo presented this afternoon. Is a composition of two functions proposed by Ferreira in a paper just a long time ago. Danilo this morning raised some concern about new distributions in survival analysis, and I'm very worried about that, and I agree with him. But Box said a long time ago, any models are wrong, but some are useful. So that's the idea I'm using here. Okay, that's my colleagues. And next, I'm going to present the summary of the outline of my talk. First of all, I like to formulate the problem, what's going on here. And the second, I propose a latent model, which has some biological interpretation to justify the new model I'm proposing here. And the third, I will formulate the main variable, the only variable I observe here, which I call first the heating time variable. And this is a negative binomial distribution. It's a very general formulation of the binomial negative distribution, which I use to propose this new model in survival analysis, which I call extended explanation J negative binomial distribution, where J is the baseline distribution I wish to flexibilize. So finally, I will give some illustration from the Bayesian point of view with some conclusions. That's the outline of my talk today. Okay. First of all, I'm going to talk about the problem. What's the real problem I try to solve here? The problem is the following. Suppose I have a random variable x, a non-negative random variable, for example, lifetime variable. And I'm supposed here the G is the distribution I am proposing for this variable, which I call the baseline distribution. And the idea is to flexibilize this distribution to get more depth fitting on the data. To get this, I'm going to propose some distribution, which I call P, as some quantity between 0 and 1. This parameter here, this omega here, will represent the biological interpretation I'm going to talk next. And beta is the parameter which will flexibilize these distributions. What do you mean by flexibility? Flexibility is the following. If I have this composition, if I have some distribution between 0 and 1, and apply to my baseline distribution, there is some quantity I call here beta 0, which my distribution is the same as the baseline distribution. So the role of the parameter beta is to flexibilize this G distribution in this sense. And the omega is responsible for the biological justification to withstand this null distribution. I introduce a new extra parameter here, a power parameter, which I call this justify this name. We exponentiate the G distribution because I want to flexibilize the exponentiate G distribution. If alpha is equal to 1, we have the baseline distribution. This is the summary of I'm trying to do. The problem here is how to find this transformation, this probability distribution to satisfy all these conditions. That's the problem. And with the purpose to focalize the biological mechanism represented by this distribution. That's the problem I will try to solve. Okay, that's the main idea of the problem. Fine. So, repeat again, I will try, the purpose is to start off with this distribution and to get a more flexible distribution in this sense here, but with a Bayesian, with a biological interpretation. Okay? What do we mean by biological interpretation? I try to use the carcinogenesis process to explain what I mean by biological interpretation. This is a simple graphic to showing what I mean by that. First of all, I have here a normal cell. This normal cell is exposed to some agents, and this normal cell is initiated by these agents. I will call here some notations. I will call here N the number of the initiated cells by some exposition of the cells from some cancer product. So the organism tries to recuperate, to repair these cells, but someone cannot. So I'm worried about the initiated cells which become damaged cells, or cells responsible for the tumor. Okay? I will call NX the number of initiated cells which become damaged between some interval between 0 and X. For fixed X, I'm worried about these damaged cells in this interval. Okay? These cells are growing, and when the number of damaged cells in this fixed interval 0x is larger or equal to some quantity, I call here R, the tumor is detected. The process is irreversible. The patient can be died from this cancer. This I call here, I said before, the shareholder problem. So this is a critical point. And this is the point where the number of damaged cells is larger or equal. This stage, this cancer is identified. So that's what I mean by carcinogenesis process, which I will use to justify from the biological point of view the model I'm going to propose here. Okay. So Next, some notations to characterize my latent model. I'm going to show here. Let n some fixed value for the number of initiate cells in the exon interval, which I will count this any initiate cells. Each cells can be unpaired or not repaired. So I'm going to do here some Bernoulli variable, which is equal 1 if we have an unrepaired cell collagen between this time. So this variable is an indicator variable which is indicating if the damaged cell is presented or not in the interval I'm observed. Otherwise, this variable is 0. That's the mean of this indicator variable. Px is the probability of the J initiate cell to become damaged in this interval for all n cells I fixed before. So now I'm going to formulate some stochastic process. This is very well-known probability in book-like failure, for example. And this compound variable is related with these two quantities, but assuming we don't know the number of the initiated cells. For example, if you have any initiated cells, this variable is counting the damaged cells between this interval. If you don't have initiate cells, suppose the patient is cured, the cancer is not present. This is very well known as a compound variable. This will be very important to introduce a more flexible model based on the baseline distribution by coherent T. Okay? The mechanism which will be very important here to get this new model, this new supermodel, is the probability generate function of this variable. It's very important to me now to connect this probability generate function of this variable with the probability generate function of this variable. But it's very well known in Felder's book, which is the proposed generate function is a composition between the probability generate function of the variable n and the probability generate function of this random variable. Okay, this is a very well-known result, which will be very important here. So, next, I'm going to formalize now what do I mean by latent model. Each variable, each latent variable has some time to become damaged, which I call here xj, xi, is the time the IS cell to become damaged. This variable, this could be between 0x or not. The proposed, the basic distribution I want to extend, I'm supposing here is a distribution which generates this time, but it's not observed. That's justification for this latent. The critical point I call here R, which is very important to identify the cancer. All are not observed, but I'm going to put some discrete probability on this variable, a geometric distribution, to generate my model. This, and I said it before, this variable is very important, very critical, because if the number of the damaged cell is greater or equal to this quantity, it can be fatal to the patient. So there is some damaged cell which will be responsible for the death of the patient or for the cancer. So, summarizing here, I have N, X, NX, R, PX. These are the elements which identify, which I call here a latent model. It's very natural here, since this variable is generated by this J distribution, assume is the probability if the cells, initiate cells to become damaged, or your promotion time, which I call here XA, is between 0x. So it's natural to define the probability if it happens to be equal to the distribution I proposed for the promotional time of this initiated cells. That's the idea of this variable. Unfortunately, all these quantities are not observed. So, what you observe? Okay. We observe here, which I call I will not for this variable for x, which is this. X is the lifetime of the patient, is the quantity I really observe. I define it here as the first instant x in which the number of the damaged cell reach this quantity, which I suppose to be greater or equal to 1, because if R is equal to 0, the patient don't have the initiated cell, damaged cell, so he will not have you die of the cancer. So from this definition, I call way the same as the order statistic or the R. And for this, based on this definition, I will call X as a first latent time. Okay, the first time I reach this kind of the stop time. Okay, so there is some strategy here. It will be very important to produce this new model, which I call here the first activation. What do we mean by first activation? When the probability of R equal 1 is equal 1. What means that? It means that the first initiated cell which becomes damaged is responsible for the death or for the cancer. That's the idea behind this definition, this assumption. Otherwise, if this probability is equal to 1, I mean all damaged cells are responsible for the cancer. So this assumption, I mean by first activation, the first cell responsible is activated, and between 0x is responsible for the cancer. Otherwise, if R equal N with probability 1, all damaged cells is responsible for the death. That's the two strategies. There is something between these two strategies. but I'm not going about that. I'm going to focus in this first strategy to get my supermodel, my model I want to flexibilize. This, I recall this variable have this xi have a G-distribution, okay? Now I'm talking about the survival analysis, the survival function, sorry, which is the probability of the cancer is detected after some time fixed x, which is equivalent to say that the number of that cells is less or equal to the number of the R-1 cells, which is critical to detect this cancer. Okay? That's the survival function I want you to look for. Well, after some simple computation, you can get some expression for this survival function in terms of the probability generated function of the nx based in 1 minus omega. What's omega here? Omega here is the parameter of the discrete distribution I am assuming for the critical point. So if W is equal 1, I am working with the first strategy, okay? So it's very important to know this parameter to identify which kind of strategy the cells are working to, the damaged cells are working to provoke the death of the patient. So this is a simple computation. Okay, here is the probability of the damaged cells equal n is 0 to infinity, and this is the probability the number of critical cells equal less greater or equal to n minus 1. If I use this distribution here, we can get this expression in a very easy way. Okay, so here I have some mechanism to obtain the survival functions for the random variable, the only variable I observe here, which is x, in terms of the G distribution and this parameter over, which is characterizing the first activation. Okay. Next, how I do with that? Using some result I published in a paper in 2021. We define the first heating time G density like the function G. G is the density function of my original density. This is some kind of weighting function. I have here some normalization. And in this paper, it's not hard to find that this quantity is a function of that parameter, I said before, and the derivative of the probability function of the variable n applied to this quantity. Here, this quantity is representing the first activation scheme. This is the biology interpretation I mean here. By using a simple mathematical manipulation, this denominator, you can find cumulative distribution which will be very useful to get to solve my original problem. So here it's not difficult to use this result here. Put the result here, we get some probability distribution between 0, 1, which is very easy to see, like a composition between P omega, which is this function, apply some quantity here. So here is applied to this unity distribution. Okay? And if you take the derivative of this quantity, you get the final density. Here we have the basic line density, I wish to apply some quantity here, which is trying to modify this distribution based in this mechanism connected to the number of initiated cells, and this parameter which is representing the first activation of the damaged cells. You can write easily this way, okay? This is a kind of thing Danilo was talking about this morning. I have some my basic distribution here, some composition here which try to modify this distribution, where the parameter only represents the first station. But how do I can to expand the distribution? This I didn't answer yet. I haven't answered yet. Let's talk about something about that. Here it has the same thing I said before. This is the probability distribution I was looking for to get my extension of the distribution. Is the best function which corresponds to the distribution. But the next step is to introduce a new parameter, which I call beta here, in order to extend the baseline distribution, the same as I said before, my first slide. That's how I can produce this new parameter. To do that, I need a very nice model. This is a very general negative binomial distribution. This is very nice distribution. This parameterization, this parameter here is E, which in my problem means the expected number of initiated cells when the patient is exposed to some agent, some hallucinations. And the beta is the parameter which is very important here because it represents the phenomenon of the dispersion or over dispersion or under dispersion here. So this parameter is called here dispersion parameter. When this is very interesting because when beta is equal 1, this is exactly the Poisson distribution. So the variance is equal to the mean. So you don't have the dispersion, super dispersion, or over dispersion, or under dispersion. So it has some independence between the cells, which is not realistic. So in this sense, this parameter is very important. This is the parameter I'm looking for to extend my baseline distribution. There is other distribution which is enclosed in this family when I change this bit. For example, this here is interesting because when beta is equal minus 1, this is exactly, I will have the baseline distribution. So this is a reason because this parameter is very important in these extensions. The next line, I have it here again now. So using this distribution, I know this probability generates function. So I use this composition I told before, and I can get this new distribution with a composition of the generated function of the variable n, which I know here on the negative binomial distribution, and composed with this function which I define here, suggested by the formula of the previous results. Conclusion. So I will go, if you apply this, since I replace this s by gx, I will have a new distribution based in two stages. So the first stage, I have to define this quantity, which is derived from the geometric distribution. This is characterized in the first activation scheme. In the second stage, here I introduce the parameter omega, the biological interpretation. Here I will introduce the negative binomial distribution in order to get some extension of the Bayesian distribution, but have some biological interpretation in terms of the variable n. It is responsible for the shape sets. Okay, that's some kind of conclusion. What I said before, I obtained this distribution from these two states. Okay. Now I want to get more general distribution, so I'm going to take a power of that distribution I got, which will be my final distribution, which I'm looking for. Which here I have some problem with this extension because unfortunately these two parameters are not identified. But I think, I'm not sure, this I try to the next page, next research, to use Bayesian some prior or some coverage to solve this problem. But here, I use some properties I might talk about here. It's possible to get an idea of this parameter here from the parameter rho, which is the mean number of initiated cells corrected by the first strategy. It's new, the mean number of initiated cells, which will really could become damaged cells. Okay, you can get some idea of this quantity. This is not exactly the solution; it is an empirical solution. But if you get some information about this new mean, if you have this transformation, you have some kind of new negative binomial, which the parameter theta is replaced by rho, but not corrected by this parameter, which could be, if you know rho and beta, you can give some idea if the first strategy is working to give the event of interest. Okay. Here I try to show you the new distribution which I obtained using these ideas in a more detailed way. For example, if this is a very complex model, it has 1, 2, 3 parameters here, and this parameter is replaced with the original parameter omega at starting theta. This is the new distribution I'm going for. If beta is equal to 0, the binomial, negative binomial distribution becomes Poisson. So this distribution looks like that, which is called exponential, exponentiated Poisson distribution. If beta is equal to this quantity, we have a very important expression which is very neuroscientific lifetime distribution could be included in this way. If you have if beta equal 1, go ahead and Marshall-Walken distribution, a very nice distribution here. And of course, if beta is equal -1, we start from the distribution, and I do not get anything more if beta is equal 1. So I have here a super model which has a very important role here. If it has some quantities that speak quantity, I can include very important models where Q here is given by this quantity. If I take where SX here, SX here is the cumulative distribution of the line distribution. Yeah, that's the model I'm looking for based on these ideas I told you. Next, here I have the density function, so I have to derive that expression like in here. If you alpha equal 1, I don't have the exponentiated model, and the corresponding density is given by this quantity, which I said before. Here's some example. For example, if you have if you how much time I have?
5 minutes.
5 minutes?
Yes.
Well, I have to skip something here.
5 minutes, not 5
Yes. Here's some graph here for I took this y distribution, some parameter. I have some behavior of the density, decreasing. It's very flexible for the y1 distribution. As you see here, we have a list of some distribution which is a particular case of that distribution. This is very recently. This is Marshall-Walken here. This is a generalized initially here, loss exponentiated, low mass distribution. And the mathematical property of that model I showed was studied by Gauss. He obtained the quantized function, moment generated function, mitigation. Gauss liked very much the mathematical property, so he used the very complicated expansions to get the results I'm going to show here because I don't have time. So I skip that. Here I have also a nice interpretation how to get the proposed model based on Box-Cox transformation. I don't have time to show this in detail, but you can summarize everything I said before. Here's the Box-Cox transformation, where P here is the probability of cure, and beta is our parameter of the negative binomial, is the parameter isolation theta. And this is the Box-Cox transformation. I can put who in terms of P, which is for Fisher transformation. I don't have time to explain here because I can show some basic stuff. Okay, here we have some illustration, but Bazin is responsible for the computation. If you have some question, please ask me. So he uses the EBEB and non-informative proper non-informative priors. This data is about 799 intervals between both along and there 5 presenting of fluid 9665. And the basic model is here. And we compare some difference model for particular values of the beta. Here, here are my non-informative drivers. There's some transformation here, gamma distribution, gamma. We use Markov MCMC strategy to obtain the results and use some criteria to see if the algorithm is converging or not. This is traditional in this Bayesian theory. And here is the result, as you see here. For illustration, I was designed to get some values for this parameter beta, if beta. The basic distribution here is the exponential variable. This is the parameter of this parameter. This corresponds to beta equal -1. This is percentile. This is the parameter of the variable distribution. Omega is the variable distribution. And I don't have it, I don't have this parameter. This is the criteria to show how this model is good. For beta equal -1, we have, for alpha equal 1, we have the variable distribution. Of course, I put alpha equal 1, we have the percentile, we have the percentile of this parameter, and omega is equal 0. I don't have the step. First step is this is the. For beta equal -1, we have the exponential, and we have the Marshall-Walken. Y is the base distribution, Marshall-Walken again, and the Marshall-Walken for supposing the exponential when this parameter is the size parameter, the size parameter is equal 1. If you look at this quantity, it seems to us this is the best model. Okay, this is our Weibull model is a Marshall-Walken exponentiated exponential Weibull for alpha equal 0.6. This is the estimation of this parameter of Weibull distribution. This is the quantity of the normal cells corrected by the first strategy. I believe with this probability the first plant cells is responsible for the cancer, and here is this one. This is only an illustration for this particular value of beta. So I have some conclusion. Now, under the proposed latent variable, it's possible to unify alternative model for the first time or any time with this one biological interpretation. We propose instead some structure proper of the same exponential. This was did by Gauss worked with this problem. Some application from to illustrate this new model which encompasses models and models provide analysis. We believe this random activation mechanism to extend the baseline solution is linked in a elegant way on the Cox transformation. Unfortunately, I didn't discuss this in detail. And the Bayesian machinery for inference problems proposed here are a new way to obtain and apply a working model with potential use in many other areas, such as the semantics or something. And here is some reference. That's it. Thank you very much.